Hey, welcome back. So, in last couple of lectures, we talked about resistors and capacitors in circuits. Today, we're going to just talk about if we have both of them in the same circuit. So this is called the RC circuit. And then we'll talk about how to charge and discharge an RC circuit. Okay, so we'll jump in. So when you have a resistor and capacitor both at the same time in the circuit, okay, so this is a power source and there's a resistor, there's a capacitor here, there's a switch. So you can imagine once you have this switch closed, then the positive charge is coming to flow out of the um, battery's positive terminal, going through this resistor, and then be deposited on this capacitor over here. And then on the other hand, negative charge will flow out from here, and then be deposited onto this positive plate. Okay. Now, in reality, it will be the electrons are flowing out here. You get minus charge, positive minus charge at the bottom plate here. And then in this case, electrons flow back in here. So then there's positive charge over here. Okay, so that's what happens. But you can see that when you have charge building on this capacitor over here, now the voltage across the capacitor will be increasing because you have more and more charges going on here. At a certain point, the voltage across this guy is going to be equal to this. So then there will be no longer potential difference between the positive terminal of the battery and this upper plate over here. So then the flow of the charge will cease. So then you would have fully charged this guy. Okay, so then you can see on the capacitor, the voltage increases as time function, and then you'll flatten out. And the same thing, for the voltage as well will increase and then flatten out. Okay, so because charge and voltage are proportional to each other. If you do Q over C, remember when we do Q over C, it should give you the capacitance, right? So C equal to Q over V, and C is a constant number, so then Q over V, Q and V should be proportional to each other. Okay, so that's what happens when you close the switch. So this process is called the charging of the capacitor. All right, this next one here. So the charge on the capacitor as a function of time t, it's the exponential function here. So it's the capacitance times the epsilon, which is the voltage provided by the battery, times 1 minus exponential to the minus t over tau. This tau is a constant number, which is equal to R times C. So this is called the time constant of the RC circuits. Okay, the voltage is similar. It's equal to just the epsilon. Okay, so EMF is for the electromotive force of this symbol, epsilon. So you can also replace this guy as the epsilon here instead of EMF. So this can be replaced just by epsilon there. Okay, it's the same as EMF, or sometimes people like to call EMF V0, and that's pretty much the same thing, just a symbol. Okay. All right. So for this equation over here, you can see after a long time when the capacitor is fully charged, so then T will equal to infinity. So exponential to the minus infinity will be actually 0. So then when the capacitor is fully charged, the charge on the capacitor should be just equal to C times epsilon. Okay, so this is the final charge on the capacitor. And then the final voltage would be just equal to epsilon. Okay, so similarly. All right. We will take a look at this example. Okay, so this one says the switch on an RC circuit is closed at t equal to 0. Given that epsilon equal to 6.0 volts, R equal to 92 ohms, and C equal to 28 microfarad, how much charge is on the capacitor at time t equal to 4.0 ms, which is milliseconds? Okay, so you can see now you have the switch closed, so you start to charge the capacitor, right? So this is the charging process of capacitor, and you're looking for how much charge is on the capacitor. So if we go back here, you will realize that this is the equation you're going to use. Okay, so this is the equation you're going to use. looking for how much charge is on the capacitor, okay, at a certain time t. So then it's just plug in numbers, okay. All right. So here we are looking for Q as a function of t, okay. So we know we should use Q as a function of t equals to C epsilon 1 minus e to the minus t over tau, which tau is equal to R times C, okay? So where tau is R times C basically. So then we basically will just plug in the numbers, okay? So C is equal to 28 micro, so it's 28 times 10 to the minus 6, okay? Minus 6 for R. And then epsilon is 6 volts, okay? E 1 minus e to the negative t. This is 4 milliseconds, so 4 times 10 to the minus 3 seconds, okay? Over R times C. R is 92 ohms times C is 28 10 to the minus 6 because it's microfarad, okay? All right, so a big bear AR parenthesis outside there. Okay, so at the end you should get so remember a few just a few unit conversions, okay? So at the end you'll get 132 1.32 times 10 to the minus 4 coulombs, okay? Or you can say 132 microcoulombs, okay? So for this guy, all right, just plug in numbers in the equation that you need to use, okay? All right. So we know that voltage increases as a function of time t, and then it'll flatten out when you are charging this capacitor, okay, in the RC circuit. Now you'll see that if you plot the voltage versus time t, you'll see that actually it charges us very quickly after the 4 times of the time constant tau. Okay, tau is equal to R times C. So then you are pretty much at about greater than 98% of the total. Okay, so in that case, the next one then will be pretty much just equal to the final voltage on here. Okay, so typically if you are doing this lab, you will say you can just stay up to maybe 4 or 5 times of time constant, then you can stop your measurement there. Okay, the charge will be the similar curve, so it will go up exponentially and then flatten out here. Okay, in that case. All right. The current in the circuit, okay, so it will actually start out with a relatively large current, which is equal to the EMF over R, and then it will die out exponentially, okay, to again almost 0 up to 4 times of time constant, okay. So the current is exponential decay function, which is epsilon R over R times e to the minus t over tau. Again, tau is the time constant over R times C, okay. So that's for the charging process. The voltage and charge goes up and flatten out, but the current goes down, okay. All right, now let's talk about discharging. Okay, so if you now remove the battery from the source and then keep the switch closed, so then the charge and energy built up on this capacitor now can be used by this resistor. Okay, so now the charge will flow through this guy and then create a current, and then go into this negative plate will neutralize the charge over there. Okay, so that's what happens. So the voltage on the capacitor will decrease. Okay, so exponentially die out. Voltage equal to V 0. There should be a sub-zero here on this guy, which is equal to the epsilon. So this can be also just written as epsilon. Okay, so in that case, all right. If it's fully charged, okay, so it'll die out and then exponentially. Again, after about 4 times of time constant, it's pretty much used up there. Okay. Okay. Let's take a look on the and then just one more comment. So um, voltage will die out, charge will also die out. Okay, so charge will also go down like this. And then the current, again, current will also go down like that. Okay, so current will decrease quickly. Okay, as well. All right, because in this case, the current is just equal to the V divided by the R. So it'll be the same exponential function. Okay. This one says there's a this figure on the left here shows a simplified circuit for a photographic flash unit. So about maybe 15, 20 years ago, digital camera was still a very famous thing. So and then in that sense, there's a flash unit. Okay, so it's made up like this circuit over here. There's a battery charge the capacitor, and then later on, the energy in the capacitor will be released to flash out the flash light to take pictures. Okay, so this circuit consists of a 9-volt battery and then 50 kilo ohms. Okay, so 10 to the minus 3 or 10 to the positive 3, and then 140 microfarad capacitor and a flashlight unit, light bulb, and 2 switches. Okay, so when switch 1 is closed, you are charging this guy, and after that you can open the switch 1, then close switch 2, so then the energy will be drawn from this capacitor, and then you'll fire the flashlight. Okay, so that's what this is about. It's asking you how much time does it take to charge the capacitor to 5. Okay, so if you need to charge this capacitor, the voltage to 5 volts, how much time does it take? Okay, so this is a charging again, not exactly discharging. So again, we'll use the equation of V, right, as a function of t. It's going to be equal to epsilon times 1 minus e to the minus t over RC, okay, which RC is tau. And we are given this is 9, and this is 4. So this guy is 9 volts. This is 5 volts. And we are looking for the time t. We know R and C. Okay, R and C are both given. And we can solve for t. Okay, so this is again basically using the equation, but you now solve for t. Okay, so we'll take a look at algebra. Okay, let me choose switch over here. All right, so the equation, we just identify the equation to use v as a function of t should be equal to epsilon 1 minus e to the minus t over r times c. Okay, and we are looking for t, so t is over there. So we set up that 5.0 volts equals to 9.0 volts times 1 minus e to the minus t over r times c. So we can calculate r times c. Maybe first r times c, we can calculate it. So r is 7. R is actually 50, 10 to the third ohms, and c is 140 times 10 to the minus 6 farad. Okay, so that actually gives us just 7. So 7 seconds. Okay, so we can do that over 7. Okay, and then we are solving for t. All right, so we can divide both sides by 9, right? By 9 volts there, 9 volts there. So get rid of that. And then this is 1 minus. Now this is just 1 minus there. On this side, you have that. Okay. So this term has t, we're going to isolate that guy. So you move 1 to the other side. So it becomes 9/5 minus 1 equals to negative of e to the minus t over 7. All right. And then now actually, excuse me, this guy will be 5/9. Okay. 5/9 minus 1. So 5/9 minus 1 gives you 4/9. Okay, so 4/9 by negative, okay, equals to negative of this. So negative becomes positive. Okay. Now t is in the exponent here. So you want to do inverse of the exponent, which is natural logarithm. Okay. So you do natural logarithm to both sides of the equation now to get rid of e. Okay. So on the right hand side will become just minus t over 7. Okay. And then on the left hand side, you have that, okay, line of that. Now you might multiply both sides by minus 7. Okay, so minus 7 and minus 7 there. Okay, so get rid of minus and 7. So then you have t equals to minus 7 line of 9/4. So punch those numbers in your calculator. This will tell you t is equal to 5.67 seconds. Okay, so it takes about 5.67 seconds to charge this unit there. So if you ever find a digital camera, you can try. You cannot like click on the flashlight constantly, right? It will take a few seconds to charge it up. Okay. All right. So going back to the slide. So that's pretty much what we learned today. So we learned about RC circuits. When you have both resistor and capacitor in the circuit, you can charge and discharge the circuit. Okay, so in the charging process, the voltage and charge goes up and then flatten down up to 4 times of time constant, where time constant is equal to R times C. For the discharging process, the voltage dies out, okay, exponentially. Also, then the charge dies out, and then the current will die out. Okay. The common thing here is the current both charge and discharge process. The current die out exponentially. Okay, so that's the same thing, but charge and voltage are the other way around. Okay. All right. So we'll stop there, and we'll see you guys in another time. Okay.